for joining. This is training session 05, and it's getting started in Lava v2. And I'm Bill Fletcher from Linaro Field Engineering. So what I'm going to cover in this session is a brief intro to Lava and installing it. I'm going to go through configuring a single instance of Lava v2. I'm going to talk quickly about virtual and physical targets, and I've got a couple of examples. I get as far as a boot test with both of those, and I'm just kind of evangelizing Lava because it's great, and you should all know about it and be using it every day. In terms of this session, so I will be talking about installing Lava and running tests. I don't expect you to follow along and install it as I speak. I bet if you do, I would be impressed. Some of you may already have it installed on your laptops, so you can obviously join in. There's a lot of detail. I'm not going to go through every configuration file. I mean, there are some eye charts I have to show you that a file exists, but we won't go into that detail. All the referenced files are at mypeople.linaro.org area. So device templates, job files, images, which work at least for me. And so if they don't work for you, then you're quite welcome to come and ping me and we'll find out what's going wrong. So this is kind of a meta tutorial. It's an invitation to have a go. Is there anybody here who's completely new to Lava? Okay, well, this slide is for you, okay? I can invite you down to the front. It's like having a birthday in the audience, you know. Okay, so Lava, new readers start here. It's the Linaro automated validation architecture. It's an automation system for deploying kernels, device tree blobs, and rootfs onto physical and virtual hardware for running tests. Anybody involved in Lava will obviously tell you can do a lot more than that, and you can probably do almost anything, but that's kind of a common use case. Let's go with that for a start. So it's very scalable. It scales to huge installations that we have in Linaro, distributed, you know, across multiple machines, you know, multiple sites in countries, multiple countries around the world. Lots more information online. There's a static docs link. And I'm going to talk about Lava v2 just in the sense that it's the latest Lava. So, you know, I've been a casual user for a couple of years with Lava, and now there's a new, stronger Lava on the street, and, you know, it's interesting to get to grips with it. There's a lot of tutorial material out there, but it tends to refer to like older versions. And I'm consciously not going to try and refer back and say the old version did it this way and the new version does it this way. I'm just going to give you an overview, a sort of out-of-box experience for this current version of Lava without necessarily going on about old ways or making comparisons. Because as time passes, that'll be less valid anyway. So there are some Lava knowledgeable people in the audience. I can see you. So do feel free to pitch in, interrupt, correct anything that I say or add detail, and questions and comments are welcome. So first of all, and this is, you know, for quite a few of these activities where there are steps to go through, like installing, I'm not going to install it live here. I've put a couple of like 1- and 2-minute videos up on YouTube. The links are here in the deck. And you can, it's just a walkthrough of doing the install or various other things, just so you can see the steps and I don't need to go through the commands. But Lava is a Debian package. It works with supported versions, Jessie and Stretch. If you install the Lava package, you get everything that you need for a single instance. It's a Python package. You find it under Python in your tree. One caveat, and this is, as packages and change and as distros change, then this sort of thing is necessary from time to time. If you want to install Lava on the stable Jessie release, then you've got to use backports. And you've got to enable backports when you do the installation. And if you don't do that, it fails in an interesting way that it doesn't actually give you the latest version, and then you just kind of subtly wonder a few days later why some things don't work. And the other caveat is that for various reasons, although it would be nice, it doesn't work on, for instance, Ubuntu Trusty 14.04 because of some dependency issues. Now, there are people doing some very cool things to make sure that you can run Lava on anything but with containers. But this is, I'm talking about in terms of a native install on a base machine. So, this is a block diagram of the basic elements of Lava. And on the right-hand side are the two fundamental blocks that make up the Lava system, the Lava infrastructure, which is one block, which is a scheduler, which handles job submission and scheduling. And it also combines or renders the target information and the test job description. So those obviously two elements of any test are what do you want to do and what do you want to run it on. And it renders that as a list of instructions which it passes to the other major block of Lava, which is called the dispatcher. And the dispatcher executes the test job actions. It manages communication to the target device, and it collects the job results. And the dispatcher is relatively dumb. It just takes the instructions, the list of instructions, the list of actions from the scheduler and does it. And that, for those of you who may have used Lava v1, that's a change. On the right-hand side are those major infrastructure blocks, and on the left-hand side are the way that you interface to them. There's a web UI, reports the results, shows the device and job status, and manages object creation and permissions. There's a command line tool called Lava Tool, which, as the name suggests, is your one-stop shop for everything in terms of day-to-day interacting with Lava. Command tool for job submission, diagnostics, and there's also a command line interface directly to the server scheduler. Now, I mentioned that Lava is very scalable. This is what it looks like if you install it on a single machine like a laptop. And actually, I have a laptop here with an instance of all that installed on one machine. But it scales. So what we call a distributed instance has the same major blocks on the right-hand side, but you can have many, many dispatchers, each one with many targets connected. So the drudgery of running the tests and interacting with the targets, you can offload to many machines. And they're all served to a single scheduler, which is managing overall the job workload to those remote workers, and they're all connected by 0MQ. The roles on the left-hand side are pretty much the same, except that the web UI keeps track of which target device instance is on which worker. So obviously you need to know if you're executing on a given target or you want to know where a given type of target is, you need to know where to find it. Now, in terms of evaluating Lava, my usual approach with different versions has been to install a single instance on a single machine. But this is the kind of setup that you would have if you were setting up a test farm or a test lab. In terms of how a test job is represented, the key concept with Lava is something called the pipeline model. A test job is modeled as a pipeline of actions. The top-level actions are deploy, boot, and test. And the pipeline structure of each job is explicit. So in terms of the description of the job in a file, you can see where the actions are. And that's the syntax describes the actions in the pipeline. The pipeline is completely visible. It's validated when you submit the job. It doesn't run through to a certain point and then find, oh, it has a problem or you didn't specify something correctly. And as I mentioned, between the scheduler and the dispatcher, it's a list of instructions that are passed. And that list of rendered instructions is something that you can inspect. If you're trying to find out why something isn't working, you can break that link and look at what's actually being rendered. And on the right-hand side are a couple of examples of, graphically what pipelines look like. So at the top level, deploy, boot, and multiple tests. And deploy has sub-steps, similarly boot, and that you can repeat maybe an action within a test, for instance, at the bottom, repeating a test 8 times. So, as I say, a simple pipeline, deploy, so download the images. For instance, if you're mounting an image over NFS, you've got Lava has to put that image somewhere where the target can access it. And then boot, so start up the target device, interrupt the bootloader, and then give it a sequence of commands to actually get an image and get it to run the test, and then to run the tests. And I don't mean to test you on individual lines of this, but this is a job file, and what I've highlighted is there's an actions section, and there's a deploy section, which has details of the images, and then there's a boot section, which tells the test job how to interact with the bootloader. So as I say, it's explicit, the pipeline concept, and the way that the job is represented in the job file match. So, I mentioned earlier that there are 2 aspects to a test job. There's the sequence of instructions that you want to carry out, and there's also how you're going to interact with the target. Now, in terms of how Lava understands the target, first of all, okay, implicit in the tool, there's the behavior of how it expects to run tests, so the hard-coded Lava behavior. And then there's a behavior which is common to many, many types of devices. For instance, if you've got a device which uses UEFI, then in terms of interacting with the boot menu or interacting with the UEFI shell, then it looks very much like any other device that runs UEFI. So those basic aspects of device behavior can be pretty much standardized. So behavior common to many device types. But then if you're running some kind of a device, devices have specific load addresses. So a specific load address for the kernel or the device tree. So you have behavior which is common to many instances of a particular type of device, and it's different from a BeagleBone to a QB truck or something. And then you have an individual instance of a device, which must be connected to something. So it must have a serial connection. It must be connected to a physical port. You have to be able to reset it. You must have some coordinates by which you can affect the state of the device. So specifics for an individual device, and then finally some aspect which may need to be specified on a per job basis. For instance, you might need to specify an extended timeout for something. Something takes a bit longer. So those are all aspects of target device behavior, but they cover different aspects of the population of devices. And actually, those categories that I listed there map onto how Lava represents target configurations internally. It has hard-coded behavior. It has a base template of behavior common to many devices. It has device type templates, so behavior for a particular device type, like QB truck. And then ways that behavior can be influenced by the job file, and ways that can be influenced by a specific device, like which serial port it has. And all that is rendered, so all the templates, plus the specifics for the job and device, rendered in something that the server gives to the dispatcher. And in terms of examples of what those things are, so common commands for bootloaders, device specific, is it 32 or 64 bits? Things which are job specific, things which are device instance specific. I mean, this covers a bit more of the detail, so you're welcome to refer to this. And these are files, template files, which reside under this dispatcher configuration. And then individual devices are not represented as configuration files, they're represented as entries in a device dictionary. So there's an internal storage representation of instances of devices. The device dictionary is a list of dictionary pairs specifying information on individual device instances. And it's something which extends the device templates, and it's something that you interact with through the command line tools. So if you want to add another device, then you do that through Lava tool. And if you want to update a device, you do that through Lava tool. Now, I wanted to go through an example device, because I think if you want to evaluate Lava, then it makes sense to download it to an individual machine, and then you want to get something up and running fairly quickly. The device that I chose was QEMU for ARM64. And again, there's a little 2-minute video of installing QEMU and getting a device up and running. And all the configuration files that I'm using for this, so the device template files, the device dictionary entry, the job file, they're all in my people.linaro.org area. Now, as I say, I chose this because I thought it would be relatively straightforward. It has its quirks. And in fact, the specification for how Lava models the QEMU ARM64 device type is still evolving. So I have something that works that I've shared. If you want to try it, you're very welcome, and we will be updating it as we go along. But the steps are: install QEMU, create a device instance in the device dictionary, and then you also need to add it to the web interface. And another caveat is that at the moment, this example works very well for a boot test, but in terms of extended testing, this is something that we're still working on. I chose QEMU because QEMU is, if you want to invoke QEMU, all you have to really do is come up with the right command line. If you've used QEMU, it has a wonderfully rich set of options. And this is the command line that I generate in Lava to run an ARM64 job. And I actually color-coded it to say which bit of the command line comes from which of the device templates or the device dictionary or the job file. So where it comes from that chain of target information. So most of it comes from the device type template. Some specifics for the device and also things like the MAC address would come from the device dictionary. And then obviously the images are in the job file because the job specifies which images it uses. And then things that are grayed out are basically Lava boilerplates, so they come from just the way that Lava works. So as I say, that command line comes from this hierarchy of how Lava models the QEMU device. And interestingly, for a virtual device, QEMU, it can run an x86 job, it can run an ARM64 job. You don't actually have to tell it what architecture it's emulating until you submit the job. And Lava actually provides the capabilities of put context, Arch ARM64. That's where Lava tells QEMU what kind of architecture it expects, and you can vary that on a per-job basis. So there's a lot of flexibility here as to where you tell Lava and how much is common and how much, let's say, is customized per job. And that ARMv64 context is a context variable inside the job file. So I've just highlighted it here, just above the actions section. So actions is a highlighted in the previous job file, but here's the context, ARM64. In terms of submitting the job file, if you've not used Lava before, again, a little video to walk you through it. Lava has a mechanism for user authentication. You need to generate an authentication token before you can submit the job, even if it's your own local instance. Once you've got that authentication token, then you add it to your local GNOME keyring using Lava tool, and then you submit test job files, again using Lava tool, referencing that authentication and the job file. So that's a very quick overview of how you would bring up something like QEMU in order to just maybe validate a Lava installation. So what you can do on a single laptop, you can install the Lava dispatcher, the Lava server, the web UI, an instance of QEMU. You could submit a job, you can boot it, and you can potentially run some tests. What's different when you want to run tests on a physical device? Well, you need some kind of serial connection to the device, or you need some sort of console. You need a way to put the system in a known state and reboot it, and you need a way to transfer the boot image to the target. So with QEMU, all those things are pretty straightforward because all the stuff is already resident on your single machine. Here, you have to specify serial, power control, and you have to include network. So for serial, the cert2net package is installed automatically because it's a dependency in Lava. And you configure an entry in the cert2net conf basically to say how Lava will talk to the console of your device. And the serial connection is specific to one device instance. You might have 20 boards of the same type, but you need to specify which serial port is which device. And so that is something which is put in the device dictionary entry. So that's something which is device instance specific. And for network, typically the dispatcher can rely on TFTP downloads, and Lava installs TFTP as dependency. The device templates actually assume DHCP, so you do need to install DHCP because it isn't a dependency, or it's not installed as standard by the package. So that's serial and network.
Quick question.
Yep.
With the specifying of the TTY, if you work with a system that has TTY ground or CUSD ones,
Yep.
is there any facility to support specifying vendor ID or product ID?
UDEV rules. UDEV rules and USB vendor and other strings.
So you want to use that to make them?
Yes. So this is actually TTY USB 47 or something, but in my UDEV rules, I recognize the vendor and the product code, and I map that onto TTY BeagleBone or TTY HighKey. But yes, otherwise it wouldn't work. It's, well, if you feel free to mail me, and we can talk more on that. Yeah. Yeah, in fact, I was saying that actually it's not installed as a dependency. So yes, you could just use what you already have. I mean, if you've just got one target and one laptop, it seems like overkill, but actually you still need it. Yes. Right, okay, so if you have a target that has multiple network connections. in fact, we have had targets that connected to a JTAG box integrated in Lava for quite a long time. So that sort of thing has already been done. But if you have a particular target, then just talk to us, and we can go through that. Is that your JTAG is the only way to talk to the target? Is there a virtual console over that? Yeah. Right. Because from the history that I know of the Lava developments, we've dealt with cases where there's been a JTAG associated with a target, and that JTAG has also had a network connection, so you've had two network devices, which you kind of need to orchestrate for one job, and that's also possible. In fact, Lava is very rich in terms of running network tests, where you have multiple sort of like a sub-network of devices that all need to have roles assigned. So yeah, we have unplumbable depth, I guess is the answer. For power control, PDU is the abbreviation in Lava speak for power distribution unit, a way to put the system in known state and reboot the board. So the assumption is that you'd have a top of rack or side of rack power distribution that you control. PDU daemon is one framework. There is at least 2 frameworks for power control now. PDU daemon is the best, but there's also an SNMP one. And so again, power control for a particular device instance is something which you need to say, this outlet controls this device. So again, it's a device dictionary aspect rather than something which is in a template. And for my own portable Lava setup, I built a PDU out of an Arduino and a relay board, and there's some details on that link. So for a physical board, my example is BeagleBone Black. So as I mentioned, the base template has instructions which are common to many devices, and many devices that run U-boot, pretty much one U-boot device looks like another U-boot device. And so those tend to reside in the base template. But then things like load addresses, which are specific to BeagleBone Black, they reside in the BeagleBone Black type template. And then in the device dictionary entry, the device specifics, which, as I mentioned on previous slides, things like serial connection, power control coordinates. And in the job file, nothing specific. So, yep.
So what is the nature of the device dictionary? Is it always is it like a shell command, or is it a set of variables, or
It looks, a device dictionary entry, I'm glad you asked, the very next slide looks like this. The syntax is Ginger2, which is sort of allied to Python templating language used for Flask and Django. Okay, so there you are. Thank you. So this is what a device dictionary entry looks like. It's Ginger. If you look at the template files that I've also been describing, they're written in the same syntax. And the syntax allows you to specify what can be overridden at a later stage in the hierarchy. Aside from maybe a few kind of the architecture of the language, but actually you've got connection command, which is the telnet connection, and you've got a power off, hard reset, and power on command. So basically, it is power coordinates and serial. And the device dictionary, that entry is imported using this Lava server command. So if you want to add an instance, it's that, well, for a physical device, It's that kind of dictionary entry which you import to tell Lava that there's this device that has these coordinates. So that was a very kind of quick walkthrough of Lava v2 and some of the newer concepts. I've got a little demo system here, which I may be able to coax into life. If you just give me a couple of seconds. I'm happy to take any questions. I appreciate that I rattled through that stuff fairly quickly. I think it is worth pointing out that there is a lot of existing tests on previous versions of Lava which need to be migrated. There are different models by which people can interact with Lava. So, for instance, they can interact with Lava as a service because we have these huge scaled instances, and so you just submit tests remotely to a remote device, to one of the test farms around the world. But at the same time, it's the same infrastructure is doing the same jobs, and if you want to have a new device added, then it's likely you'd be interacting with the Lava lab team to talk through how the device would be configured through the chain of files that I've been describing. So this is my little local Lava instance. I've actually got two devices configured on my laptop here. This is the web interface for Lava. Apologies that the lighting is not great. Maybe I'll just tip it back there. Which has a list of jobs, and then here in my little case, I've got a BeagleBone Black center stage and a small switch. I've got power control and a USB hub, and I've got a number of jobs. I maybe kick off some more jobs. So, for instance, a QEMU job and a BeagleBone Black job. And so you can, well, if I move my camera, my chair, then I've actually got focus is not great. I've got two running jobs, one of which is on the internal QEMU instance, which is running on the laptop, and one of which is running on the BeagleBone Black, which is connected here. And after about a minute, if you were very, very quiet, you'd hear the relay click for the power control. But you'll just have to take my word for it if you're at the back. So we can come back to that and see if they've actually successfully completed.
Just out of curiosity, is your BeagleBone Black loading server via TFTP?
It's loading the kernel and device tree via TFTP, and the root FS is mounted over NFS, which Lava all sets up for you, actually. So I have a... If you want to see the picture of how Lava works, this was an exercise for me whilst I was putting this together. So the ways that Lava interacts with the target is Sir2net I've mentioned, TFTP I've mentioned. It deals with NFS, and obviously it has power control. So those are all functions allied to the dispatcher. So just by way of a quick summary, so I'm pleased to say that my QEMU job is completed, my BeagleBone Black job is still running. So, two example devices, plenty of resources, online associated with this, so I encourage you to go and have a little look, watch a few of the videos to get an idea of how it works, how it all fits together. For QEMU, we are looking at how we put the command line options, some within the job, some within the template, because for QEMU, you can decide things very late in the chain as to what options you want. And so that's evolving. BeagleBone Black, I would say, is very much a very smooth out-of-box experience with Lava. If you wanted a platform to actually get started with a physical one, then if you get a BeagleBone Black and you put the Debian version of U-boot on it, most important, then you'll find that it kind of just works. But it is worth pointing out that it's quite involved if you are changing target aspects. That maybe that may get smoother with time, or some helpers may be written. So if you're trying to integrate a new device in Lava, hopefully this gives you an idea of where things are, but obviously talk to us. So feel free to download an instance, install it, check it works with a known good device, and then talk to us about how to integrate a new device. Okay, and just to prove it works, so my job that I submitted on the BeagleBone, which is the top one, again, sorry for the focus, but anyway, has completed, and my QEMU job has completed, so it does actually work. And feel free to wander down and pull apart my demo, because I don't need it anymore after this session. That's all I have. Thank you very much. If you've got any questions, feel free. If you've got any hard questions, Neil, the tech lead for Lava, has got his hand up at the back. So if you want to know anything about Lava, now is your opportunity to ask it. Sorry?
What is the context used for?
So, I'm going to pass that back to Neil, because he gave a much better explanation than me.
So the context you specify in the job submission is one of the ways you can provide extra variables to the templating that actually provides the final device configuration. So it's used with QEMU to specify things like the architecture, because we allow QEMU to run multiple different kinds of jobs, and it's down to the files you supply as to which architecture QEMU should try and boot those using. So you specify that, and then the templates sort out which command line to use for those files according to the architecture you specified.
Does that mean that things in the device dictionary use that by some variable name? Or?
Yeah, so the way it works, you've got hard-coded values in the template. You've also got variables in the template. If you set a value for a variable in the device dictionary, that rules out any further changes to that variable. So it's a way of admins controlling what kind of access is actually allowed on particular devices. And then if the variables that are still exposed can be set in the context of the test job submission. So it allows a little bit of fine-grained control for particular use cases and particular ideals.
So, does that have anything at all to do with Lava selecting what targets to run the test on?
No. So, all of the selection criteria are going to be down to your submission rights, the device type you've asked for, and any device tags that you've specified. So the job submission can specify tags. Tags are specified by the admins. They are labels with descriptions that mean that generally some extra bit of hardware has been attached. So you might actually have a SATA drive attached to a QB truck in one particular case and not in other cases. So that's what the scheduler does to work out which device of the specified types It works on have you got access, and then which device is next available, does that have the appropriate tags?
Framework, sorry. Are you currently using the V2 framework to automate your OpenStack deployment for like multi-node on real targets?
That's a good question. That would be, I don't know what jobs are running in the lab. I don't know what jobs are running in the lab. I'm looking at Maria, but she's avoiding my eyes. Oh, yeah, I can see that from here. Yeah, thanks. I don't know. We'll find out. Because it's a case of what's migrated and between V1 and V2. I'm not sure what the status is. Anybody know?
So more details on how we migrate from V1 to V2 will be in my talk tomorrow, I think it is. I'll have to double check in Pathable to work. The Lava V2 migration talk. So I'll go through in detail there which, not only how we do the migration, but which device types have already got support and what is being enabled in the next round. But actually there's very few devices now that are in the main Lava production in the Cambridge lab. There are very few devices that can't go to V2.
But I think Diane's question was basically what leg you're testing, what the enterprise group are running on at the moment.
I'd have to check on what the OpenStack ones are actually using, because the OpenStack usage was quite specialized, and but there are lots of other use cases used by leg, some of which are way down on the firmware level. So, and they are happy with what they've got, because that can be done. So the
So we have KVM in the staging environment that is using multi-node jobs, but I'm not sure if they are actually running OpenStack at the moment, because, as I said, it is quite specialized. So we need to check that.
As soon as you start doing anything that is actually involving multi-node, everything becomes more complex. We can't make it any easier than, well, we can't reduce the complexity any further. It's a case of multi-node becomes a complex test job just by the fact that you've got multiple devices. So when you're starting with V2 or starting with Lava in any sense, get a really good handle on how it works for single device jobs before you start thinking about how you're actually going to do multi-node, because it really will stretch your understanding, and you need to go through the docs, which we are improving.
But Diane, I can update you as to what the latest status is. I can update you as to what the latest status is.
So you talked about the docs. I looked through some of them, but my question is there a complete definition of the schema for the job file?
Yes.
I mean,
yes, there is, because I've seen it.
okay.
So there is a limited schema on submission which goes through and checks some basic syntax checks. We had problems with V1 where it tried to be all-encompassing. It tried to generate one set of rules that covered all possible test jobs. That became part of the reason why V1 became a problem. So we're avoiding that with V2, and it's a case of each time you generate a pipeline, that pipeline is specific to that test job submission, and each pipeline is separate unless for each time you change the submission. So there are rules for each of those, and it's the validation step that happens as the job starts that is the final arbiter of whether your test job submission contains all the relevant information.
But that's not answering the question. We know there is not yet a complete schema description in the docs. It's one of the things that we're working on. I'm the person writing the docs, and I've been beating Neil up over this for the last couple of months, as I'm sure he'll agree. It's coming soon.
I guess my question is, I saw 4 commands that related to external, tools that are used for PDU and serial control and networking. Is that exhaustive, or how many different commands are there total that Lava may invoke?
Commands you can invoke from something like the device dictionary, or commands you can invoke as a part of the way the test job runs?
Yes.
Where you've got things like the connection command and power off, power on, those are arbitrary shell commands. They are scripts that lab admins has come up with their own and just replace that in the dictionary. In which bit of config?
I guess, okay, so let me describe a system I've used in the past.
Yeah.
Okay, at Sony internally we have a tool called TTC, and we defined approximately, I think we defined a total of 13 actions that we were going to put abstractions for in the tool. And those were the thing, they were very, very similar. It's like, how do you connect to the target? How do you get serial console? How do you create a login account on it? How do you get a file? How do you put a file? So that was the level of abstraction, and we boiled it down to a particular interface that we had. I'm just wondering if you have the same type of idea, like how many of those types of verbs or abstractions do you have in Lava?
Right, so those in Lava V2 boil down to the deployment methods that we support. So as new devices come along, we might need to add more deployment methods. But for example, at the moment, we've got Tumperfest, which is what QEMU uses. You've got TFTP, which is what Bill has demonstrated with the Big One Black. Then you've got Fastboot for some of the ADB devices. Then we've got some of the more esoteric ones. You've got SSH, which is way of doing a connection to a running device, whether that device is actually part of a multi-node group or a standalone device is down to the admins. Then we've got ways of accessing secondary media devices, media storage on the device. So that could be USB or SATA. Those kinds of things are where the bootloader can't actually write to that media itself. So you boot up into something sensible like a RAM disk and then write to it and then spawn off and reboot into that one. So I have got a review at the moment which is actually going through building the full list of dispatcher actions. But it really is meant to be something that you dip into as a reference rather than having a full coverage.
Right. Okay, thank you.
I guess the other thing is as we kind of generate a few more examples, and that gives people a good idea of what sort of coverage there is.
Steve does keep hitting me over the head for more worked examples. We will get there. It's a case of, a lot of the time the worked example gets delayed because we really need to have the full stack of steps behind it. We need to know or we need to describe how the artifacts used in that job were built, because one of the next questions people do when they see a worked example is how do I modify it? And if they can only modify the test job submission or the test shell actions, that's not as ideal. So It's getting the full stack. We are building a set of these standard jobs, and wherever we can, we get the full build history, we get the full log of how that kernel was built, or how the NFS was constructed, and all this kind of stuff, and all the you can see how that was actually done. It's not a small task to build a set of examples that deep.
I think we're kind of out of time here, so we need to take this gent to the bar and just buy him more beer. So thanks very much. It was been great to be able to present this and have somebody else answer all the questions. Thank you very much.